This is 6.2.2, part 1, ideal gases. Now, an ideal gas are monatomic gases, so they only have translational kinetic energies, but no rotational kinetic energies. Now, for a fixed mass of gas, the equation PV, pressure times volume, divided by its temperature, is a constant. Where pressure, P is pressure, measured in pascals. V is volume, measured in meters cubed. And T is temperature, measured in Kelvin. Now, this relationship of PV over T is a constant gives rise to an equation where if a gas that's trapped within a container changes in some way, we can relate its initial conditions to its final conditions. So we say that P1 V1 over T1 is equal to P2 V2 over T2. Right, we'll start with now Boyle's law, because to get to this relation, we use 3 different experiments and 3 different laws. So start with Boyle's law. So we have some air. And we have attached to that a pressure gauge. And then we have a column. For example, it could be a column of mercury. So by moving this column up and down, we can change the volume of the air. And by changing the volume of the air, we can also read changes in pressure. So we change pressure and volume, or we change volume and measure pressure. So change V and measure P to obtain a set of results. Now these changes, we make them slowly, because if we were to change the volume and pressure too quickly, then the temperature of the gas will change inside. But we're just trying to relate pressure and volume together without changing temperature. So if we make these changes slowly, even slight variations in temperature, it will come to equilibrium by itself anyway. So it will remain at constant temperature. Now, we make an assumption on the relationship. So we assume that pressure is equal to some constant times by volume to some integer. And then we plot a graph of our results. And plot graph. We plot a log graph. Or what we can do is, instead of using a log graph, we can do it on normal graph, but we have to log our values to change that behavior. So if we log the whole thing, we get log P equals to log kV to the n. And then we apply our log rules. So if you have two things multiplied, you separate them into two logs. So log P equals to log V to the n plus log K. Then with the power, if you have something to the power of something, you can bring that out of the log and times it. So we've got log P equals to n log V plus log K. Now you can use logs, you can use luns, it doesn't make a difference. So now, when you've got this, and what you plot on the axes is log of P is on your y-axis, log of V is on your x-axis, which means that n is the gradient, plus log K is your vertical intercept. Now if you get these results, and you do exactly this, you will get a value of n which equals to -1. So the results give n equals to -1. So if n is equal to -1, we've got P equals to K V to the n. Therefore, P equals to K over V, because to the power of -1 means to bring it down. Now, K, which was log of K, that's just an intercept, which means it's just a constant. So in this case, that K is still a constant. Now rearranging this, if we bring the V over to the other side, so it rearranges to PV equals to K, which is a constant. Now, from all of this, we can get a definition. So the gas was trapped inside a container. No additional gas molecules were able to come into the container. No gas molecules were able to leave the container. So the mass of gas was fixed. So our definition starts with, for a fixed mass of gas, and we kept the temperature the same the whole time. So it's for a fixed mass of gas at constant temperature. the pressure was inversely proportional to volume. Pressure is inversely proportional to volume. Put a box around that. Now what that meant in simple terms is you keep temperature the same, then P and V relate to each other as P1 V1 equals to P2 V2. Because P times V was a constant, whether that's PV in its initial conditions or PV in its final conditions, they're equal to the same constant because K don't change. Because we had a set of results for P and V. We plotted that line from a set of results. So doesn't matter what that set of results were, we had different values for P and different values for V, but K and N were constants, where N was found to be -1, and K is just some arbitrary constant for now, although it does have a value that we'll look at later on. Okay, let's move on. So start a new page. Next, we're looking at the pressure law. So for this one, we have a round bottom flask with some gas inside it within a water bath. And we've got a thermometer. And a pressure gauge. So in this case, the container of our gas can't change because it's a fixed container. So the volume of gas remains constant. However, because we have a water bath, we can heat the water bath slowly. And if we heat the water bath slowly, then we can assume that over time, if we keep that water bath at constant temperature, that the gas inside of that water bath will also reach that same temperature. So we add heat into there. So if I want to, for example, measure the water, so the gas, I want to measure its pressure when it's at 30 degrees C. I'll heat the water to 30 degrees C in a water bath. I will keep the water at 30 degrees C for an extended period of time. That extended period of time allows that heat to then go into the gas through conduction, which is not a very easy process because gases aren't that good at conducting heat, but over time it will. So as long as we keep that water at 30 degrees C, eventually the gas and the water will reach thermal equilibrium. So we can change the temperature and measure the pressure while keeping the volume fixed. So we say heat up water slowly and measure T and P to obtain a set of results. We make a similar assumption. So we assume P equals to K T to the N. and we plot a log graph. So we log everything again. Log P equals to log KT to the N. So similarly, again, we separate these logs. That becomes log T to the N plus log K. Then we take the N outside. So we've got log P equals to N log T plus log K. So just like last time, it's Y equals to M X plus C. So if you obtained a set of results and you actually did this graph, you would find, so results give N equals to 1. And if we have N equals to 1, then you put that into the equation above. P equals to KT to the 1. Therefore, P equals to KT. And that gives us pressure over temperature is equal to some constant. So just like before, we can now define the pressure law. So again, the whole system was sealed. No gas was able to come in to the system. No gas was able to leave the system. So we had a fixed mass of gas again. So the pressure law is, for a fixed mass of gas, and in this case, the volume never changes. So for a fixed mass of gas at constant volume, pressure is directly proportional to temperature. Put a box around that. So if P over T is a constant value, that means the initial values of P over T is equal to the final values of P over T, because it's a constant. So that means that P1 over T1 equals to P2 over T2. And the conditions are that we have a fixed volume. Now, start a new page. And we're doing Charles' law. So for Charles' law, we're again going to have a water bath. And we have a capillary tube. With some air inside it. And we have a small amount of sulfuric acid in there. So in this case, the pressure remains constant because the sulfuric acid is on top of that column of air. If the air's temperature increases, then its volume will change. So normally if it was a sealed system, completely sealed system, without any flexibility, like the round bottom flask which is made of glass, then the volume doesn't change. But in this case, if you heat up the air and you expect its pressure to increase, what would actually happen is the air will expand and cause the sulfuric acid to move up. But that air is still holding that sulfuric acid above itself. So the pressure is coming from the weight of that sulfuric acid. So in this case, the pressure remains constant, but the volume and temperature are able to change. So we've got water and a thermometer, and we apply heat. So for Charles' law, we heat up the water slowly. And again, we do that slowly to ensure that the air inside the capillary tube and the water are at thermal equilibrium, so they're at the same temperature. If you heat it too quickly, then they won't be at the same temperature because it takes some time for conduction to happen into air. So we heat up the water slowly. And then by measuring the height of the air, or where the sulfuric acid is, we can measure the volume of that air in the capillary tube. So we heat up the water slowly, we measure volume and temperature. So measure V and T to obtain a set of results. So here we can assume that V is equal to Kt to the N, and we plot a log graph. So we've got log V equals to log Kt to the N. Again, we expand those logs just as we've done before. Log T to the N plus log K. So we've got log V equals to N log T plus log K. Using the actual results, we plot Y equals to mx plus C. And then we find from actual results, actual data, that in this case N equals to 1. So from results, N equals to 1. So then we've got V equals to Kt to the power of 1. Therefore, we've got V over T is equal to K, where K is a constant. And then we can define this the same as before. So, no gas was allowed to come into the system, no gas was able to leave the system. So for a fixed mass of gas, And in this case, we kept the pressure constant. So for a fixed mass of gas at constant pressure, volume is directly proportional to temperature. Put a box around that. So, just like before, if we keep pressure constant and V over T is a constant, that means that the initial conditions for V over T is equal to the final conditions of V over T. So V1 over T1 equals to V2 over T2. And if all three of them are changing, then we go back to the first equation I gave, which was PV over T equals to some constant, which gives us P1 V1 over T1 equals to P2 V2 over T2. Now, start a new page. If we go back to our readings of pressure and temperature, we can use these results to obtain a value for absolute zero. So pressure and temperature. So if we plot a graph of pressure in pascals against temperature in degrees C, if the molecules in the gas stop moving, then they stop colliding with the walls of the container. And if they stop colliding with the walls of the container, there's no change of momentum. If there's no change of momentum, then there's no rate of change of momentum. And force is the rate of change of momentum. So if the gas does not apply a force onto the walls of the container, then the gas no longer has any pressure. So if we have some results for pressure and temperature, which in real life would look something like this, we can extrapolate these results and draw a line that extends all the way until it reaches zero pressure. So if we draw a straight line with these results that goes all the way until we get to zero pressure, we'll find from this graph that this value here is minus 273.15. And that is equal to 0 Kelvin. So at zero pressure, particles are not moving. So they have a temperature of absolute zero. because they have no kinetic energy. Now at this point, they also occupy a negligible volume because they stop moving. And that is the end of part 1 of 6.2.2.